Emilian Nica.
Oh. Should I start sharing, Joe?
Yeah, please.
Okay. Okay. Yeah, can you see my slides or?
Yes, and it looks good. And please feel free to start.
Okay, so before I start, I'd like to thank the organizers for giving me a chance to talk about some of this recent work, which is on multi-orbital singlet pairing and D plus D superconductivity in iron chalcogenides and beyond. This was work done in collaboration with Chimiao, and this is it's based on these papers shown here. So I'd like to start off by discussing correlation effects in the iron chalcogenides. These are very nicely illustrated by this phase diagram, which involves a strong orbital selective correlation and even an orbital selected mod phase in this regime. It shows large mass enhancements, which can reach up to a factor of about 40. And also the observation of Hubbard bands, which of course are signal mod Hubbard physics in this regime, in these compounds. So the next ingredient, which is important to what I'll be discussing later on, is the existence of competing interactions in the iron chalcogenides. And I think these can be relatively straightforwardly understood because of similar nearest neighbor and next nearest neighbor exchange couplings. These typically lead to quasi-degenerate A1G and B1G pairing channel, which can be illustrated in a number of calculations. This is one such examples. Here we're showing the pairing amplitude. And we see that when J1 and J2 are comparable, then the S wave A1G and the D wave B1G will have comparable pairing amplitudes. And before moving on, I also wanted to mention that a similar picture actually emerges from sort of weak coupling type arguments. So it's good, I think, that these this picture is fairly common, I think. So also this quasi-degeneracy, together with the multi-band nature of these iron chalcogenides, is likely to lead to non-trivial pairing, as I'll be discussing in later slides. So we briefly talked about bulk iron selenides, but the real star of my talk are really the alkaline iron selenides, and these have a TC of about 30 Kelvin, which was shown in a number of experiments. Also, we expect the similar pairing symmetry arguments to hold in the lithium iron intercalated compounds, as well as the single layer iron selenide on STO, with the mention that the alkaline iron selenides actually have an additional electron, a small electron pocket at the Brillouin zone center, which for our purposes actually can serve as a sort of a diagnostic tool for the symmetry of the pairing function. Okay, so ARPES in these compounds shows large electron pockets near the Brillouin zone edge, but also a quite small electron pocket near the Brillouin zone center. And also in the superconducting state, one sees a completely gapped Fermi surface, including the small pocket near the center of the Brillouin zone, as indicated here with the blue. In blue, and also in this other study, we see a full gap all along this electron pocket at the center. So this really is consistent with the nodeless S wave. Now, the inelastic neutron scattering actually shows resonances at pi and pi half, and as shown here. And one needs to note that in the absence of any kind of large pockets near the Brillouin zone center, which are replaced with small electron pockets. The way that this would come about is really due to a order parameter which changes signs between the pockets at the edge of the Brillouin zone, as shown indeed on this figure. This was also confirmed by other studies. So we here have this picture that we have in-gap spin resonance and absence of hole pockets near the gamma point. And so we really require pairing with changes sign under pi half rotation. That is a sort of a typical D wave picture. Okay, so to summarize the experimental results so far, we saw that ARPES showed a gapped Fermi surface, which would normally be associated with a conventional S wave. Whereas we see resonances in the inelastic neutron scattering spectrum, this would be associated with a conventional D wave. So these seemingly contradictory results point out to the fact that these alkaline iron selenides seem to be multi-band superconductors, which are defying the dichotomy between conventional S and D waves. And there is no indication of something like time reversal symmetry breaking in these compounds. So we really want to look for general pairing candidates which have a full gap. And the sign change under pi half rotation. And importantly, we want to do so while preserving the point group and time reversal symmetries of the system. So D plus D in general, we can first consider pairing candidates which are trivial in band space, say something like a single band, or pairings which are generally independent of the band index. This would be D plus ID, S plus D, or S plus ID. And these, in general, will provide a gapped pairing and also change signs due to their D components. However, these, of course, break time reversal and point group symmetry. So we want to look instead at pairing candidates which are non-trivial in band space. And the state that I'll be focusing on is the D plus D, which has both inter and intra-band D wave pairing. And this is illustrated in the general form shown here. There's a dx squared minus y squared form factor along the diagonals, and a dxy form factors for the off diagonal pairings. This can be succinctly written like this in terms of the alpha 3 and alpha 1 Pauli matrices. So it's important to remember that this D plus D pairing belongs to a single irreducible representation and thus preserves both point group and time reversal symmetry, and that is by construction. Okay, so how would this work in the alkaline iron selenides? Well, it turns out that this D plus D in the band basis has a form very similar to the one I'd shown previously. Again, we have an intraband D wave, and this will be proportional to a dx squared minus y squared form factor, which transforms as a B1G representation. The other form factor is proportional to a dxy D wave, which transforms as a B2G. And we can illustrate how this works if we look at a cartoon version of the Fermi surface, and we see that the intraband D wave has nodes along the diagonal, whereas the interband D wave has nodes along the axis. So one can define something like an effective gap, which is given by the addition in quadrature of these two form factors. This is never vanishes on the Fermi surface. So we reach the conclusion that this type of D plus D pairing always induces a finite gap on the Fermi surface for this type of Fermi surface. Okay, so D plus D pairing in the band basis is quite natural for interpreting the experimental results, but as far as the symmetry of the pairing and the microscopic models are concerned, the orbital basis is of course much more convenient. So we can illustrate this by considering the an S tau 3 pairing in dxz dyz orbital basis, which has this form with the S wave form factor, which transforms trivially under the point group, and a tau 3 2x2 Pauli matrix in orbital space, which actually transforms as a B1G irreducible representation. So it's actually D wave like. Of course, the whole thing is spin singlet. This S tau 3 pairing transforms as a single irreducible B1G representation of the point group. And in the band basis, the same pairing S-3 in the band basis has the form that I've shown previously. And the reason for this is because the tie binding part of our Hamiltonian generically includes tau1 and tau3 matrices and will not commute with the S-3 pairing, resulting basically in these two components. So in conclusion, on this slide, S-3 is a microscopic realization of D plus D pairing in the alkaline iron selenides, and so preserves both point group and time reversal symmetries. So it turns out that S-3 can be stabilized in a 5-orbital TJ1J2 model. And this is illustrated by this phase diagram where there's an S-3 really sandwiched between more conventional phases. This requires quite strong orbital selectivity, as I've briefly hinted at in the introduction. What we mean in this case is that the pairing effectively determined by the exchange coupling J's is really dominant in the dxz and dyz orbital space. And this is illustrated on the phase diagram by this y-axis, which is actually a ratio between the exchange interactions in the xy versus the same for the xz-yz sectors. And also, we require quasi-degenerate A1G and B1G channels. So we really expect that, or we see that this phase is stabilized when J1 is roughly equal to J2. And this is illustrated in this phase diagram by the x-axis, which is the ratio J1 over J2. And we see that S-3 is really stabilized near this regime. This same behavior can also be illustrated by looking at the pairing amplitude for the various symmetry allowed channels. Again, as a function of J1, J2. On this side, we see dominant A1G channel, and on the other, we see dominant B1G. So S-3, which is given by the solid red squares, is really stabilized at the boundary between these two regimes. And we can also illustrate the properties of S-3 by looking at directly at the results of the calculations. So we see what we're plotting here is the intraband component of S-3 dominated phase for the band, which actually gives the delta pockets. And we see that this pairing changes signs between the two delta pockets as expected. And this leads to a resonance in the spin dynamics for this S-3 pairing, basically an in-gap type of resonance in this case. So collectively, this really showed that D plus D pairing, which is realized by S-3 pairing in the alkaline iron selenides, is energetically competitive, will induce a gap Fermi surface, which is the S-wave-like feature we were looking for, but also give an in-gap spin resonance, which is the D-wave feature we wanted to see. So this while also preserving point group and time reversal symmetries. So we see that D plus D pairing in the form of S-3 is actually a pretty good candidate for the alkaline iron selenides. So next I want to talk about a somewhat a remarkable and surprising analogy between D plus D pairing and the phases of superfluid helium-3. B in particular. So D plus D involves distinct D waves via non-trivial structure in band space, whereas helium-3B involves distinct P waves via non-trivial structure in spin space because it's a spin triplet pairing. So these can be set side by side. So this is the form of D plus D that I've shown initially, and this is of course the well-known form of helium-3B type of pairing. D plus D involves distinct intra and intraband D waves, whereas helium-3B involves distinct equal and opposite spin P waves. The D waves will add in quadrature to produce a full gap in 2 dimensions. The P waves add in quadrature to produce a full gap in 3 dimensions. D plus D preserves point group and time reversal symmetry, whereas helium-3B preserves the largest residual symmetry group in superfluid helium-3. So a similar analogy actually also holds for D plus D intraband only. That is, this is a trivial in-band space, involves distinct D waves. And the helium-3A, which involves distinct P waves, are essentially a trivial structure in spin space. So this two order parameters can be cast side by side. D plus ID will have basically a trivial form in band basis, and we can cast helium-3A in a sort of a similar form. These involves intraband pairing only, whereas helium-3A involves equal spin pairing only. D plus ID breaks point group and time reversal symmetry, whereas helium-3A breaks orbital spin rotation and time reversal symmetry. However, there are, of course, differences. D plus ID will be gapped generically in 2D, whereas helium-3A will have nodes in 3D. So the analogy is not exact, but it's still, I think, pretty good. And so what these analogy really establishes is that the D plus D is a natural gapped pairing state which preserves point group and time reversal symmetry. And we've shown how this can be energetically competitive in the alkaline iron selenide. So we saw that D plus D is a natural candidate for gapped superconductor with a gapped Fermi surface, which are also sign changing and which preserve point group and time reversal symmetry. And we showed how the alkaline iron selenides are a good example of this. However, one can ask, are there any other correlated multi-band superconductor which might show similar phenomenology and thus be likely candidates for this type of D plus D pairing? And it turns out remarkably that the heavy fermion superconductor cerium copper 2 silicon 2 is actually one example of this. So cerium copper 2 silicon 2 was the first ever discovered unconventional superconductor with a TC of about 600 millikelvin. And for a long time, it was believed to be a pretty canonical example of a D-wave superconductor with 9 nodes for measurements above about 100 Kelvin. So these types of experiments included nuclear spin lattice relaxation rates, thermal conductivity, as well as angle resolved upper critical fields, and perhaps most importantly for our discussion, resonance in the inelastic neutron scattering spectrum. However, this D-wave pictures was recently challenged by experiments going below 100 millikelvin, which point towards a full gap. These included specific heat measurements, London penetration depth, and even the nuclear spin relaxation rate below this temperature range. And in addition, we want to note that the phenomenological D plus D pairing actually provided a good fit to both specific heat and superfluid density, as is shown from these plots in the red line. And you know, there's actually a much more detailed discussion that I would invite you to check out by seeing this philosophical magazine paper. So what we want to do then, since the phenomenological D plus D pairing actually provided a good fit to experiment, is we want to propose a microscopic state for D plus D pairing in cerium copper 2 silicon 2. And more precisely, we want to look for the analog of the tau3 matrix in the alkaline iron selenides. So in order to do so, we must account for the orbital and spin structure, which is rather specific to these compounds. So we have quasi-localized cerium F electrons, which to a good approximation are gamma 7 Kramer's doublet due to strong spin-orbit coupling and crystal field effects. And also we want to include conduction electrons, mainly from the copper orbitals, d orbitals, which really can transform as either gamma 6 or gamma 7 Kramer's doublets. So we want to look for matrix pairing. Again, the emphasis is on matrix in the space of 4x4 matrices, which are spanned by these FC doublets. These should belong to a non-trivial one-dimensional irreducible representation of the point group. And in particular, we want them to change signs under pi half rotation. And we want these matrices to be anti-symmetric because the overall pairing has to be even parity. So we can first consider FF matrix pairings, which is typically the strongest, the product of two gamma-7 doublets decomposes as shown here. It can already exclude gamma-5 representation, which is two-dimensional, and gamma-2 representation because the matrix corresponding to it is actually symmetric. And the only representation that is really allowed under our constraints is gamma-1, and that is essentially a trivial representation. So this type of FF pairing would really correspond to the sort of canonical B1G like D wave, in which we're not interested here. So we want to look instead of at FC matrix pairing. This is expected to be weaker, but can open a gap. And to construct these, we consider conduction electrons which transform as a gamma-6 doublet, while the F electrons would transform as a gamma-7 doublet. And to see how this comes about, we can look at the copper plane in the unit. So we can take linear combination of the copper D states to get the states which transform as Px and Py. And then when we consider the spin degrees of freedom, we can take additional linear combination. And so we can build these gamma-6 doublets for the conduction electrons. And the product of the gamma-6 and gamma-7 doublets in this case decomposes like this. And we really see that this gamma-3 irreducible representation, which actually corresponds to I chi2 Pauli matrix in this CF space, is the analog of B1G representation or the tau3 Pauli matrix in the alkaline iron selenides. And so together with the overall S-wave form factor, which transforms trivially under the point group, and this 2x2 matrix in doublet space, which is a gamma-3 irreducible representation, this pairing state is really the analog of S-3 in cerium copper 2 silicon 2. And with that, I would like to leave you my conclusion slide, and thank you for your attention.
Okay, thank you, Emil. Nice talk. Any questions, comments? Daniel?
Yeah, thank you for that talk. So there's one part I didn't really understand, and I think maybe there's something I missed. So you have, you call a D plus D state, and that has some sort of orbital structure that is like xy plus x squared minus y squared. And of course, xy and x squared minus y squared are different representations in a tetragonal system. Mm-hmm. Are these being multiplied by some k-dependent factors to make sure they belong to the same symmetry channel?
You mean in this picture right here?
Yeah.
Right. So it turns out that these alpha-3 matrices transform under the point group themselves. These are matrices in band space.
Oh, in band space.
Right. So then they actually do transform such that the products between these two will make the whole thing be B1G for the alkaline iron selenide. This is actually discussed in this MPJ paper from 2021. It's a good question though, yeah. So.
Oh, I see. Okay, maybe it's something else. I mean, in the band bases, typically everything is sort of symmetric, right? So how do you get different symmetry channel? I'll take a look at your paper. There's something I'm missing there.
Right.
Yeah, I'll just see if I can understand it by reading what you wrote. And the follow-up question is, it looks like you were trying to also to construct x squared minus y squared pairing states or xy pairing states that were nodeless, right? Mm-hmm. And in the talk I just gave, we generated nodes in these states by adding a spin orbit coupling term. Is there something analogous in your theory that generates nodes? And is there some corresponding energy scale? For example, I had to have delta was bigger than some spin orbit energy scale to be sure I was nodeless. Is there something in your case that is analogous to that?
Yes, I mean, it turns out that if the band splitting generically near one of these pockets is much larger, the band splitting meaning here between predominantly XZ, YZ type bands is much larger than the pairing, then we expect to see nodes.
I see. Okay.
Yeah. But that's not, I mean, that is not the case in the alkaline iron selenides. So,
okay,
yeah.
Thank you.
And by the way, I should mention that the nodes that appear are actually, and this is like a very important point, the nodes that appear are always away from the Fermi surface. So that is a very important point, which I should stress. Yeah.
Sure. Okay. Thank you.
Ilya?
Yes, thank you. I actually have a question similar to Daniel, but more towards the experiment, because when you were, I simply not very much familiar with this alkaline doped materials, but you were showing a Fermi surfaces and it was showing an overall B1G symmetry. But I was wondering, I guess that they also have a 2 iron P unit cell. So in principle, these Fermi surfaces would also flip onto each other because, because
right, so
okay.
You mean
so
this is a 1 iron, yes, this is a 1 iron unit cell. Yeah, so
okay, and then I guess the question is the same like Daniel was asking, because in principle this is a sign changing gap, but when you flop your D wave where the pockets are flip on each other, then there will be an issue depending on the spin orbit coupling. You will have node or you will not have nodes. I see. But I have another question. So when you mentioned that you have for the story for the same story for the Therium copper 2 silicon 2, I guess that still you have an unconventional superconductivity, right? So it means that the gap is still changing sign between various portion of the Fermi surface.
Right.
Is it right? Because I have, you know, there is this experimental follow-up by Matsuda group where they used a point-like impurities, and they have shown that the TC doesn't change at all. And that would be, I guess that in this case, if you add a point like impurity, still the overall superconductivity is unconventional. So there will be a pair breaking effect. So TC would be still suppressed.
right, so I think then this issue, I would refer to you, by the way, this issue is actually discussed in some detail in this paper. And it's shown there essentially, or the arguments are that this is a very strong coupling type pairing, which my understanding was that was shown is less sensitive to these type of pair breaking effects.
I see.
Yeah.
Okay.
So
Yeah.
this would make this type of pairing, I think, more robust. But I would refer to you, frankly, to this paper, which actually has a much more detailed discussion of this point.
I see. Okay.
I think it's quite the same point that you're raising.
Okay, any other questions or comments? If not, I think this is a good point to close. Let's thank both Emil and Daniel for a good session on the multi-band, multi-orbital pairing states.